All right, can you guys hear me?
Yes.
Okay, so let's get started. So in the pre-lecture video for today, we went over um, a few basic definitions. So we talked about the axis of rotation of an object, which is basically just the imaginary line about which the object is rotating. Then we talked about angular position and angular velocity and arc length. So I'll just quickly remind you what these things are. Um, Let's quickly recapitulate. So basically, if an object is going around in a circle, so if you have this point mass which is going around in a circle, then the position vector will always have a fixed length, right? So because it's going around in a circle, the length of the position vector will simply be the radius of the circle. So in order to keep track of the position of the object, all you need is just this angle that the position vector makes with some reference direction, which you usually take to be the positive x-axis. So this angle will be enough to know the position of the particle because you know that it's always going in a circle. And this angle is called the angular position. So theta is the angular position. All right. And then if you have an object that goes from an initial angular position of theta naught to a final angular position of theta, so this angle is theta, the bigger one, then the change in the angular position is called the angular displacement. So this is very analogous. This discussion is very, very analogous to the things that we learned in chapter 2. So we went from position, then we learned about displacement, then we learned about velocity, then we learned about acceleration. That's exactly what we're going to do today. So the discussion is going to be exactly analogous. So the change in angular position is the angular displacement. And as you would expect, that's just the final angular position minus the initial angular position, right? All right. Okay, so now suppose the particle moves from point A to point B along the circle. Then another question is, and the radius of the circle is r. So that's the magnitude of its position vector. So another question is, what distance does it cover along the circle? So what is the length of arc that it covers along the circle? So let's call this distance as delta s. So that's the length of arc between the points A and B. And in the video, I explained that delta s, the arc length, is going to be r times delta theta. And where does this formula come from? What's the name of this famous formula?
Is this the arc length formula?
Yes, it's called the arc length formula. And what's one very important thing to be careful to remember regarding the angle in the arc length formula?
It's always in radians.
It's always in radians. So this only holds in radians, right? So it will not hold in degrees. Radians, a radian is a pure number, so it doesn't have any units. And a radian is basically defined from this formula. So in this formula, the angle has to be in radians. All right, so that's the length of arc, and that is going to cover as it goes from point A to point B. All right, so what else did we talk about in the pre-lecture video? So we talked about that. All right, so suppose this angle is really tiny. So if this delta theta is really, really, really tiny, then we call it d theta. And so that would mean that the points A and B are practically sitting right next to each other on the circle. So they're separated by 1 nanometer or something like that. So then the very tiny angle made by the two radius vectors would be d theta. And the arc length in that case would be ds would be with
So, how about that airplane food?
I like peanuts.
I'm more partial to the pretzels myself.
I actually, yeah, I turned 20 in like 5 days, but I refuse to celebrate my birthday while I'm taking these classes. So
I turned 19 today, so choice. Oh, Professor, I think you're muted.
All right. So, okay, I somehow got cut out. I just got back now. Can you guys hear me all right now?
Yes, sir. You're good.
Okay. All right. Okay. Is it somebody's birthday? I just got that conversation.
Oh yeah,
No.
today's my birthday.
Oh, happy
Really?
birthday. All right.
Oh.
Okay. All right. So what I was saying is that suppose the points A and B are very, very, very close to each other. So in that case, what would you say is the direction? Yes.
Also, Professor, I think you forgot to share your screen again.
Oh,
yeah.
That's ridiculous. Okay. All right. Okay, all right. So this is what I've been drawing this entire time. At least is better than that one time last year when I was teaching online for one of the very first times. I forgot to unmute myself, and so I went on talking for about 10 minutes, and I also wasn't checking the chat at all, and so I didn't notice that the chat is blowing up and everybody is trying to signal me and let me know that they can't hear me at all. And so I went on talking for 10 minutes, and then I asked a question, and I was waiting for people to reply and nobody was replying. And I was thinking that, nobody has been paying attention. And then I realized that I've been muted this entire time. So that's why I always start my lectures by asking if everybody can hear me. All right, anyway, so at least you were able to hear me, even though you weren't able to see my screen this time. So so is everybody clear about all this? I've just been recapitulating what's in the pre-lecture video. So I talked about what delta theta is, and I talked about delta S, which is the length of arc as you go from point A to B. And also, the question that I just asked is that if points B and A are very, very close to each other, which means that the angle delta theta is infinitesimal, then what can you tell me about the direction of ds?
The direction would basically be straight.
Yes, exactly. So it would be straight and it would be along the tangent, along the tangent at A. That makes sense? So ds would be along the tangential direction. If the point B is practically right next to the point A, then if you draw a line through them, it will be along the tangent. Do all of you understand that? Okay, so ds would be in the tangential direction. We'll use this fact a lot today. Direction. All right. Okay, so what is the direction of ds? It's along the tangential direction. All right, so the next thing that we're going to talk about is how fast is this angle theta changing, or how fast is theta changing? So that is a quantity that is the quantity that describes that is called omega, the angular velocity. And you can define an average angular velocity as follows. It's the change in the angle theta divided by the time it took for that change to happen. So it's delta theta divided by delta t is your average omega. That makes sense? Usually we are interested in the instantaneous omega at a certain point of time. And so that is written just by omega. And when I just say omega, I usually just mean instantaneous omega. And that is simply delta theta divided by delta t, same way you define all instantaneous quantities, the limit delta t tending to 0. Just to remind you, all that means is that you are now talking about the omega at one particular instant of time, say t equals 7 seconds. So in order to find that, you still do delta theta divided by delta t, but you make the delta t to be a very, very tiny interval surrounding t equals 7 seconds. So something like 6.999999 to 7.000001, something like that. So you make the delta t as tiny as you can to get the omega at that particular instant. And we know, we've discussed this extensively before, we know that that is nothing but d theta dt. So omega is d theta dt, right? the next thing that we talked about, oh, and when omega is constant, that means theta is changing in a uniform way, and that is just uniform circular motion. In fact, we had briefly met omega in chapter 3 when we were doing that that multi-part problem, where we were studying uniform circular motion. So when omega is constant, it is uniform circular motion. But in this chapter, we are not going to restrict ourselves to just uniform circular motion. So omega is allowed to be variable, which means that sometimes the angle theta might be changing fast, sometimes it might be changing slow. It's not necessarily changing at a fixed rate. Okay, so we talked about omega. All right. Okay, let's look at this problem. So I'll give you a moment to read this. So what this problem is saying is that you've got an object that's moving in a circle. It's following the circular path. This is the center of the circle. If the object undergoes an infinitesimal displacement d theta, so the object is over here and it moves from here to here, and just imagine that this angle is infinitesimally small, very, 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 very tiny. You want to find the displacement vector of the object, which is kind of what we were just talking about. So you want to find this displacement dr, and you want to express that as a vector. And I've given you some unit vectors that you can use to express this as a vector. Remember that when something goes around in a circle, we usually choose axis along the radial direction and along the tangential direction. So I've given you a radial unit vector, which is r hat. And I've also given you a tangential unit vector. The traditional symbol for that is theta hat. So I've just given you that, it's just a unit vector in the tangential direction. So in terms of these unit vectors, what is the displacement vector dr, assuming that the displacement, the angular displacement d theta is very, very tiny. Everybody understand the question? Okay, so d theta is very, very small, right? So as we just discussed, the points A and B are practically next to each other on the circle, right? So that means the line joining A and B is really just on the tangent to the line. There's really no curvature there at all because it's so tiny. So the line joining A to B lies on the tangent. That makes sense? So that means this dr is really just in the tangential direction. Is that clear to all of you? Because the displacement, angular displacement is infinitesimal. So dr would be entirely in the tangential direction. It will not have any component in the radial direction. And what is the magnitude of this dr? We just talked about that in terms of r and d theta. What's the length, the actual length of the dr?
That'd be r d theta.
Exactly. R d theta would be its length, and we just decided that its direction will be along the tangent, which means that the vector dr would just be, can somebody tell me what it would be in vector notation with these two unit vectors that I've given you? Just the way you would write I hat something plus j hat something. In this case, you have r hat and theta hat. That's the only difference.
Do you have r d theta t hat?
Yes, exactly. That clear to all of you? So there is no component in the along the radial axis at all. There's only a component along the tangential axis. So the unit vector in the tangential axis is theta hat, though in an old version of the PowerPoint, I might have had t hat. So theta hat times r d theta. That's all. Plus r hat times 0. There is no component in the radial direction. That makes sense? And so that's the answer to the question. So if you want to express the displacement, vector of the particle as a vector, it's just going to be entirely in the tangential direction, and its magnitude is going to be r d theta. That clear to all of you? All right, so we found the displacement, the infinitesimal displacement vector of the particle for a very, very tiny angular displacement d theta. The displacement is dr, right? So now we can actually find the velocity. This is the same velocity that we've been talking about from the beginning of the course. Remember that velocity is defined as dr dt from chapter 3. Everybody remember that? So since we found dr, we can just divide it by dt, which is the time taken for that displacement to happen, and we get the velocity of the particle, right? So let's do that. So it's theta hat r d theta is what we just found for dr. Divide that by dt, and that's our velocity vector. And so the velocity vector is theta hat, r is a constant. What is d theta over dt?
Is that omega?
Yes, it's omega. So we get theta hat times r omega. That makes sense? So the magnitude of the velocity, which is the speed of the particle as it's going around in the circle, is given by r multiplied by omega, right? And what is the direction of the velocity? It's in the tangential direction. This fact we had derived in other ways back in chapter 3. We knew that the speed of the particle as it's going around in a circle was r times omega. We had figured that out. And we also knew that the velocity is in the tangential direction. We just derived the same result in a slightly more elegant way over here. That clear to all of you? So the velocity vector is theta hat times r omega, or the magnitude of the velocity vector, which is the speed, is just r times omega. Right? Okay, so we found the velocity vector, and I did that over here. So I'm just calling this t hat as theta hat. I just renamed it. T hat is really not very common. It's usually called theta hat, but it doesn't matter what you call it. We are not going to use the tangential unit vector anymore after this. So the velocity is in the tangential direction. So it's theta hat, and its magnitude is r times omega. All right. One thing you can see about the velocity of an object that's going around in a circle, for the same omega, the magnitude of the velocity or the speed is different. So if you have an object that's over here, its velocity will be r times omega. But if you have an object that's further out over here, it will have a faster speed along the circle because r is larger for that particle. That makes sense? So for the same omega, the speed at which it's going around in the circle is going to be different. That clear to all of you? Okay, and this velocity v, just because we have we have an angular velocity as well, which is omega, this velocity v in this chapter, we are going to always call it the tangential velocity. It's the same velocity that we've been studying so far, dr dt, that's its definition. But in this chapter, we are going to call it tangential velocity just because there is another velocity here. That makes sense? Just like in a class, when you have two students with the same name, then you have to have some kind of other way of identifying them. So you mention their last name or something like that to distinguish between them. So that's why we are going to call this same velocity as tangential velocity in this chapter to distinguish it from the angular velocity omega that we learned about earlier. That clear to all of you? All right. So let's do a quick example just to make sure we're clear about tangential velocity. So let's take a look at this problem. Give you a moment to read it. Okay, so you've got this merry-go-round. It's moving at a constant. Its constant operational speed is 1 complete rotation in 45 seconds. Now, what quantity is that? What quantity does that relate to? The different quantities that we learned today. The fact that it's doing 1 complete rotation in 45 seconds.
Is that equivalent to our average omega?
Yes, exactly. It's the angular velocity of the object. It measures how fast the merry-go-round is spinning. So it's basically omega, but it's given in different units. We are told that it does 1 complete rotation in 45 seconds. We can use that to figure out what the omega is. Omega is delta theta divided by delta t. Strictly speaking, that's average omega. It's delta theta divided by delta t. So, but in this case, omega is constant. So average and instantaneous mean the same thing because it's not changing at all, right? So omega is equal to delta theta divided by delta t. 1 complete rotation, what is that in radians? We want to find the omega in radians per second because that's the most standard unit that we're going to use. So what is the delta theta when it does 1 complete rotation? How much does the angle change by?
2 pi.
2 pi, exactly. And what is the time it takes to make that change?
45 seconds.
45 seconds. So 2 pi divided by 45 seconds. So whatever that comes to, radians per second. What is that in radians per second?
0.14.
0.14. So we found omega. Now we have to find the angular speed and the tangential speed of each child. So we are given the distance at which the two horses are. What would the angular speeds of the two horses be? The omegas. So just imagine this merry-go-round is spinning. You've got one horse over here, another one over here. So we found the omega of the entire merry-go-round. What's the omega of each horse?
Would it be the radius of each horse times the omega?
No, that would, we are looking for the omega. That would be the V that you're talking about. That's the next thing that we are going to find. But what is the omega, the angle of each horse going to be? Do we need to do any calculations for that? The answer is no, because everything is rotating together, right? So they all have the same omega. That makes sense? So suppose at a certain instant, the two horses, 1 and 2, are over here. Next instant, when the merry-go-round rotates by a certain angle, the first horse will be over here, the second one will be over here. So they'll both trace out exactly the same angle in the same amount of time. So they're all going to have the same omega because they're rotating together. That makes sense? So the omegas of the two horses are going to be the same as 0.14 radians per second. Is everybody clear about that? All right, the next question is, what is the tangential velocity or tangential speed of each child? So that is the speed of each of these horses as they're going along the circle. So for that, you use the result V is equal to R omega. That makes sense? So what is the velocity in meters per second or a speed of horse number 1? It's going to be 3 multiplied by 0.14. 3 is meters and 0.14 is radians per second. Radian is unitless. So it's going to be 0.42 meters per second. Meters per second is exactly what you'd expect for a velocity or a speed. That makes sense? And the other horse, which is at a greater distance of 6 meters, will have double that. It's going to be 6 times 0.14. So it's going to be double of that. Is that completely clear to all of you? All right. Okay, so this one was worked out over here on the slide. All right. So I told you that in this chapter, we are not restricting ourselves to uniform circular motion, which means that omega need not be constant. So the speed at which it's rotating could be changing, right? The quantity that measures how fast omega is changing is called the angular acceleration. So there are two ways, there are two flavors of the angular acceleration. It comes in 2 flavors, just like all the other quantities. You can have an average angular acceleration, which is simply the change in omega divided by the change in time. So that's the average angular acceleration. The symbol for angular acceleration is alpha. All right, so alpha average is delta omega divided by delta t, but usually we are more interested in the instantaneous alpha, which is exactly the same, defined in exactly the same way we've defined all our instantaneous quantities. It's just delta omega divided by delta t, with delta t tending to 0. So once again, you're taking a very, very, very tiny interval of time surrounding the moment of time at which you want to find the alpha. So you do delta omega divided by delta t over very, very tiny interval of time. And that is nothing but the derivative of omega. So we get this very important relationship that alpha is equal to d omega dt. And earlier we had seen that omega is equal to d theta dt. You can see how analogous this is to our discussion in chapter 2. In chapter 2, we talked about position. It was x, and velocity was dx dt, and acceleration was dv dt. And this is exactly analogous to that. That clear to all of you? All right. The unit of omega was radians per second, and the unit of alpha is radians per second, right? Because it's delta omega divided by delta t. So it's radians per second square is the unit of alpha. Is everybody clear about alpha? So omega measures how fast the theta is changing, and alpha measures how fast omega is changing. Right? It's angular acceleration. Okay, now when an object is not uh, executing uniform circular motion, so suppose you have an object which is going around in a circle, and it's not uniform circular motion. So if it's not uniform circular motion, then its velocity over here and its velocity over here might have completely different magnitudes. So if it's uniform circular motion, the velocity always has a fixed magnitude. It moves with a fixed speed around the circle. But if it's not uniform circular motion, its velocity at different points in the circle is not going to be the same. That makes sense? So if its velocity along the circle is changing, there must be some acceleration which is directed in the tangential direction, which is changing its velocity, its speed in the tangential direction, right? So if it's not uniform circular motion, there must be some acceleration. So if it's not uniform circular motion, there must be some acceleration in the tangential direction. And that acceleration is responsible for changing its speed in the tangential direction, right? And so that acceleration is called the tangential acceleration, a sub t, okay? So a sub t is its acceleration in the tangential direction. We can easily derive an expression for a sub t. So okay, we can do it like, I'll do it over here. So its velocity in the tangential direction is v. A sub t just measures how fast its tangential velocity is changing. So a sub t is defined as dv dt. It's the rate at which its velocity in the tangential direction is changing. We just derived an expression for v, which is r omega. You can just plug that in. So d dt of r omega is a sub t. And so r is the constant always because it's circular motion. You can pull that out of the derivative. And so you get r times d omega dt. And what did we just say this d omega dt is?
Angular acceleration.
Angular acceleration. So we get this expression a sub t is equal to r times alpha. So this is the relationship between angular acceleration that we just saw and the tangential acceleration. So please make sure you're clear about what these accelerations mean. The tangential acceleration is responsible for changing the velocity, the magnitude of the velocity as the object goes around in the circle. So because of tangential acceleration, it's not uniform circular motion. The speed along the circle is changing. And angular acceleration measures how fast omega is changing, right? And these two are related as a tangential is equal to r alpha. Okay. Now, so since it's not uniform circular motion, there is an acceleration in the tangential direction, a sub t, and that acceleration, as we just discussed, is responsible for changing the speed along the circle. But any object that's moving in a circle already has another component of acceleration, which we've talked about earlier, much earlier. What is that?
Would that be in centripetal acceleration?
Yes, our old friend, the centripetal acceleration. We can't forget that. So anything that's moving in a circle has to have a centripetal acceleration at all times, right? That's responsible for making it move in a circle in the first place. So in addition to its tangential acceleration, the object also has a centripetal acceleration, a sub c. So we can see that its total acceleration has two components, one in the tangential direction and the other in the radially inward direction. And these two components are a sub t and a sub c. So if I'm interested in finding the magnitude of the total acceleration, what would that be in terms of a sub t and a sub c?
Would it be a sub t squared plus a sub c?
Yes, exactly. It is simply you would simply combine these two components to get the original acceleration vector. It's going to be a sub t square plus a sub c square, square root of that. That clear to all of you? So that is the tangential vector. If you want, you can also write a sub t as, if you want to write it strictly as a vector, this is the theta hat unit vector. The unit vector in this direction is theta hat, and this is the r hat unit vector. So just as an exercise in vectors, what would this the a total vector be in terms of these unit vectors?
Would be r hat plus theta hat.
You have to like, so I'm asking, you have the two components of a vector, and I'm just asking you to put it in the I hat something plus j hat something form, except that instead of I hat and j hat, I have r hat and theta hat. So what would that be? So it would be r hat something plus theta hat something. And so what would that be?
Oh, r hat AC plus AT.
Yeah, and typically the direction of r hat is radially outwards, typically. So it's minus r hat a sub c plus theta hat a sub t. Though we are really not going to use this form at all. It's just an exercise in writing a vector, that's all. That clear to all of you? And the magnitude of a total is simply the square root of the sum of the squares of the two components. All right, so that is the tangential acceleration. And we've just seen that the centripetal acceleration, there's also the centripetal acceleration, which is v squared over r. You can also write the v squared over r as omega square r, because we know that v is equal to r omega. So that's another way of writing a sub c. And the total acceleration is the vector sum of a t and ac. So a total is equal to square root of at square plus ac square. Everybody clear about this? All right, so we've talked about a bunch of different velocities and accelerations. So let's do a couple of exercises just to make sure that we're cleared about all this. Let's try this top hat question. Let's put it up on top hat. Okay, so it should be on top hat now. All right, please put in your answers. Okay, so I'm closing the poll now. Let's see what you guys did. So the correct answer, so the question is asking, an object moving in a circular path will always have, right? So always have, the correct answer is A. It will always have a centripetal acceleration, because the centripetal acceleration is essential for it to move along that curved path. Without the centripetal acceleration, it would just move in a straight line. So the centripetal acceleration is responsible for it to move in a curved path. When does it have tangential acceleration in addition to centripetal acceleration?
When it's not in uniform circular motion.
Very good. That's exactly correct. When it's not moving in uniform circular motion, then its speed along the circle is changing, right? Uniform circular motion, it always moves with a fixed speed along the circle. That's what we studied in chapter 3. But when it's not moving in uniform circular motion, its speed point to point along the circle is changing. So in order to accomplish that, it needs an acceleration in the tangential direction as well. So the tangential acceleration changes its speed in the tangential direction. So that makes it non-uniform circular motion. So the centripetal acceleration is always there. That's required for it to go in a circular path or any kind of curved path. But the tangential acceleration is there when it's not uniform circular motion. Right? The example we studied in chapter 3 was uniform circular motion. So there was no tangential acceleration in that particular case. Is that clear to all of you? All right. let's do a problem where we calculate a bunch of these things just to make sure that we are, again, absolutely clear about all these different concepts. Okay, so I'll let you think about this for a moment. All right, so let's think about this problem. A pendulum is, you're given the mass of the bob of the pendulum, and you have the length of the thread, and so it's swinging in a vertical plane, right? All right, and it's released from rest, and when the thread makes this particular angle with the vertical, you're given the speed at which the bob is moving. So what we are told is that there is this pendulum, and it's been released from rest from a horizontal position. So the bob is tracing out this circular arc. When the speed of the bob is, so when the bob is in this position, you're given the angle that it's at right now. And you're also given the speed of the bob at that instant. And that's given to be 2.06 meters per second. Okay. And you're given the length of the pendulum, L. All right. It's probably easier if I just work in symbols. So it's just going to be V naught. All right. So the first question is asking.
Sorry, Professor, I just had a quick question.
Yeah.
So when we have a problem like this, how do we know whether they're asking for the angle on one side of the pendulum or the other?
What's the other possibility? Oh, why did I not draw it like this? You mean? Is that your question?
Yeah, how do we know if we're solving for, like, for example, if we're solving for theta or that angle that's next to theta on the right-hand side?
Oh, why is it not this angle? Yeah, it doesn't make any difference if you take this angle.
Okay.
Yeah, it doesn't make any difference at all. So you can pick either one. Okay. So so I just randomly picked the right-hand side, but if you pick the left-hand side, it doesn't make any difference at all. So so we know the length of the pendulum. It's 0.25 meters. And we know the speed at which it's moving when it's making this particular angle, and that is 2.06 meters per second. All right. So the first question is asking, and you're given the mass of the bob. So this m is given. So the first question is asking, what is the magnitude of the bob's angular velocity omega and tangential velocity v? These are the two things that we need to find out in the first part of the question. Does anybody want to give that a try? So how would I find either of these, any one of these two?
Don't they already give you the velocity and the tangential?
Yes, exactly. So this 2.06 meters per second is nothing but the tangential velocity of the bob. That makes sense? So that is already given. So this Vt is simply 2.06 meters per second. That's exactly what the tangential velocity is. The speed of the object along its circular path. So that the speed with direction is velocity, and just the magnitude is just the speed. So we already know the tangential velocity. Is there any way I can find the omega from here? How would I find that? Look at all the relationships we've derived today. I'll write them down for you. So omega was d theta dt, and then v was r omega, and alpha was d omega dt, and a tangential was r alpha. So these are the relationships we derived. A centripetal is, what's the formula for a centripetal? We derived that a long time ago.
V squared over
V squared over r, exactly. All right, so yeah, so these are all the formulas we have. So is there any way I can find omega?
Yes, you can use velocity is equal to your radius times omega.
Yeah, v is equal to r omega. So omega would just be this v tangential divided by the length, which is the radius. That makes sense? The second part of the problem is saying, find the centripetal acceleration. So how would I find that? At this instant, when it's at this position, let's call it A. So how would I find its centripetal acceleration?
V squared over R.
Exactly. So the centripetal acceleration would be V squared over R. And what direction does the centripetal acceleration point?
Radially inward.
Radially inward, exactly. So that is the second question. The third question is, what is the tangential acceleration of the bob? So we know that this is, would you say that this is uniform circular motion?
No,
No. Why is it not uniform circular motion?
because our acceleration in the tangential is an acceleration.
There will be an acceleration in the tangential direction. And you also know that if you just from experience, if you swing a pendulum, you know that it's going to speed up as it's moving down, right? It'll be moving fastest at the bottom, and then it's going to slow down as it goes up and stop. So it's not moving with a fixed speed at all. So it's not uniform circular motion. So there must be an acceleration in the tangential direction. How do we find that acceleration? To do that, we have to use Newton's second law. And this is a calculation we've already done in chapter 5. So you've already seen this calculation. So to find the tangential acceleration, to find any acceleration in general, you use Newton's second law, because acceleration comes from force. So we just need to see what force is acting in the tangential direction. And from there, we can use Newton's second law and find the acceleration. So we're going to redo a calculation, which we've already done in chapter 5. So what are the forces acting on the bob when it's at this location?
You have tension acting.
Yeah. And what else?
Gravity.
Tension, and what's the other one?
Gravity.
Gravity, very good. So just as we've done many times before, we are going to choose our axis. One will be in the radial, the other one will be in the tangential direction. Which force do we need to break into components?
Gravitational force.
Yeah. So mg, there'll be one component like this, another component in the tangential direction. That tangential component is the one that we are interested in for now, but we might as well just, as an exercise, we might as well just write down Newton's second law again. So this one will be mg cosine theta, and this one will be mg sine theta. Let's write down Newton's second law. F net equals mass times acceleration, both in the radial and the tangential directions. So let's start with the radial direction. So in the radial direction, can somebody tell me with the proper sign convention what equation I get? What's the F net part in the radial direction? This is all old stuff, nothing new here at all.
It's negative mg cosine theta.
Radially inwards is positive. Very good. So go ahead. Yeah. So I have that, and then anything else? Any other force in the radial direction?
Oh, and plus tension.
Exactly. So T minus mg cosine theta is equal to mass times, what's the acceleration in the radial direction?
Your centripetal acceleration.
Exactly, which is v squared divided by r. V is the instantaneous velocity at that particular location. V squared divided by r. All right, so I'll call it L instead of r, because that's the radius in this case. That makes sense? And in the tangential direction, we'll just choose this direction to be our positive direction, right? So can somebody give me the expression for Newton's second law in the tangential direction?
Would that be mg sine theta is equal to mat?
Exactly. So there is only one force in the tangential direction, and that is mg sine theta. And that is equal to mass times our unknown tangential acceleration. And so from here, we can solve for the tangential acceleration, which is what this question is asking for, g sine theta. So you can see that the tangential acceleration is going to be g sine theta, right? And that's the answer. So AT in this case is g sine theta, and it came from applying Newton's second law. Is everybody clear about that? So we have the Bob's tangential acceleration, that's part 3. Part 4 is asking for its angular acceleration, alpha. So How would I find alpha if I know its tangential acceleration?
Could you find it by dividing that tangential acceleration by our
Exactly. We would just use this equation right here. That alpha is a tangential divided by r, which in this case is L, right? So we found the angular acceleration alpha. The next part is asking for the total acceleration. How would I find that?
Square root of at plus at squared plus ac squared.
Exactly. So the total acceleration means that the acceleration vector of which the two components are at and ac, right? And so the total acceleration is simply ac square plus at square. The magnitude of the total acceleration is ac square plus at square, as we just saw in our discussion right here. So that's the total acceleration. The sixth part is asking for the tension in the cord. So how would I find that?
You can use the equation that you wrote down for Newton's second law.
Exactly. So that is not connected to this chapter. It's a chapter 4 and 5 question. So I've already applied Newton's second law, and I found this equation in the radial direction. I could use this equation to solve for the tension. So the tension would simply be T is equal to mg cosine theta plus mv squared divided by L. So that was not related to this question, this chapter. And finally, another question that I just put in, it might not be in your version of the PowerPoint, is the velocity of the bob when it reaches the bottom. How would I find that? So I know the velocity of the bob when it's at point A. How would I know the velocity of the bob when it gets to point B?
Could you divide theta by the time it takes to get from A to B?
Well, that would give me an average speed, right? But I'm interested in the instantaneous velocity at point B. So how would I find that? Can we use anything from anywhere in the course? Maybe chapter 6 and 7?
Could we use like K naught plus U naught equals
Yes,
MU?
exactly. Absolutely. We can definitely use conservation of energy to answer that. So we know what its velocity is at position A. We need to find its velocity at position B. So we can set up conservation of energy. So I'll just draw a separate diagram over here. We know its velocity over here. We want to find its velocity when it gets to the bottom. So this is a chapter 6 and 7 question. How would we do it? Okay, so we need to know the difference in height. So let this height be h. This is L. This is also L, right? The radius of the circle. So K naught plus U naught plus W other equals K final plus U final, right? So the initial kinetic energy, what's the initial kinetic energy at location A? So this is just a review of what we did yesterday. So what's the initial kinetic energy at location A? In terms of its velocity, v naught.
1/2 m v naught squared.
1/2 m v naught squared. In terms of the height h, we'll choose h equals 0 at the level of B. So U is equal to 0 at the level of B. So in terms of the height h, what is the potential energy at location A? What was the formula for potential energy?
mgh.
Yeah, so it's going to be mgh, right? Is there any W other in this problem? No. The kinetic energy at B is what I'm interested in. So that's 1/2 mv squared, right? And what is the potential energy at B?
0.
0, exactly. So now I can solve for this V. The only thing I don't know is this H, right? Now, if you think back to the very first pre-lecture video that we had even before this course started, in the very first PowerPoint, there was a problem, a trig problem, where we actually calculated this H. And I would recommend that you go back and look at that or look at your notes for that if you've forgotten. But if this angle is theta, then this H, does anybody remember what this H comes out to? So it's just a trig question. So Does anybody remember what this comes out to in terms of L and theta?
Is it L minus L cosine theta?
Yeah, it's L times 1 minus cosine theta. And I showed this in a lot of detail in that very first pre-lecture video. So that's a useful relationship. And so you can use that to get rid of H. And so you get 1/2 mv0 square plus mg. Instead of H, you write L times 1 minus cosine theta is equal to 1/2 mv square. And then I'll let you finish the algebra yourself over here and you solve for v. That makes sense? So that is how you can get the velocity when it reaches the bottom. And so the last two parts of this problem are just review of stuff that we've done earlier. Is everybody clear about this? The main point of this problem was to calculate all these quantities that we just discussed today, so you have more of a feel for what these quantities are and how to get them. That clear to all of you? All right. So I think it's probably now a good time to take a break. So 2:01, 2:06 is when we'll resume. All right, so let's get started. So, okay. So we talked about all this. All right, so now let's just look at the analogy between linear quantities and rotational quantities, and hopefully that will help you put this information, organize this information in your head. So we're going to look at linear quantities, which we studied earlier, and we're going to look at rotational quantities for an object that's going around in a circle. So let's start with position, and then we'll talk about displacement, then velocity, and then acceleration. All right, so for an object that's going around in a circle, the distance that it's going along the circle, that linear quantity is arc length is denoted by s, right? So that's the distance traveled along the circle. And what is the angular quantity which determines its position? So this is s. What is the angular quantity that determines its position?
That'd be theta.
Yes, theta. That makes sense? So I should just say angular. That's probably better. All right. Displacement along the circle is delta s. And what is the corresponding angular quantity that measures the angular displacement? So if this angle changes from theta initial to theta final, what do we?
Delta theta.
Delta theta, which is the angular displacement. That makes sense? All right. Velocity, the speed at which it's moving along the circular path, that is the angular velocity, that is the tangential velocity, which is v, right? I could write v sub ta for tangential, but it's not necessarily because the velocity is always in the tangential direction for an object going around in a circle. So we just call this the tangential velocity and call it v, and use the symbol v, I mean. And what is the corresponding angular quantity that measures how fast it's going around in the circle, or how fast omega is changing? I'm sorry, how fast theta is changing, not omega.
Omega.
Yes, exactly. So omega measures the rate of change of theta, right? So omega is d theta dt. It'll probably make this too cluttered if I put that over here. Now, while we are doing this, we might as well also look at the relationships between these quantities. What is an equation that connects s and theta?
Arc length.
Yes, s is equal to r theta. The same equation will obviously connect delta s and delta theta. So delta s is equal to r delta theta. What is the equation that we derive that connects v and omega?
Your tangential velocity is equal to r omega.
V is equal to r omega, exactly. All right. Okay, let's move on to acceleration. So what is the quantity that measures for an object moving in the circle, what is the quantity that measures how fast its tangential velocity is changing?
Tangential acceleration.
Exactly, a tangential, right? And what is the quantity that measures how fast omega is changing, the rate of change of omega?
Alpha.
Exactly, alpha. That makes sense. And what relationship did we derive between a tangential and alpha?
That alpha is equal to a tangential divided by r.
Yes, or a tangential is equal to r alpha. That makes sense? So you can see that these linear quantities and angular quantities are exactly analogous to each other. And I might as well just put this over here. So omega is equal to d theta dt, and alpha is defined as d omega dt. That's the definition of alpha, the rate of change of omega, right? Okay, now think back to what we learned in chapter 2. In chapter 2, essentially, we learned all these linear quantities, position, velocity, acceleration. And then we saw that when the, okay, so we also had v is equal to dx dt and a is equal to dv dt for one-dimensional motion. We saw that if the acceleration is not constant, then if you want to find the velocity and the position, then you have to use calculus, right? But if the acceleration was constant, we had kinematic equations which linked the velocity and the acceleration and the position. That makes sense? So we can do exactly the same thing over here as well. So suppose you have a particle that's going around in a circle, and its initial at t equals 0, its initial position is theta naught. At some future time, its final position is theta final. And its initial angular velocity was omega naught. And at some future time, its final angular velocity is omega, right? It's not uniform circular motion, so omega is changing. And maybe it has an angular acceleration alpha, which happens to be constant. So if alpha is constant, then you can derive the same kinematic equations for all the angular quantities as well. So it's kinematics reloaded. If you thought you're done with kinematics, you're never done with anything in this course. Everything just keeps coming back. So you have kinematic equations for the angular quantities as well. And so I'll write down the linear kinematic equations, which you should have memorized by now. V final is equal to V initial plus AT. X final is equal to X initial plus V0 t plus half AT square, and V final squared is equal to V initial square plus 2A X minus X0. All right, these were the linear kinematic equations. Now, using this analogy that we have over here, can you tell me, you probably have this in your own notes, but I'll have to scroll up. Can you tell me what the linear angular kinematic equations are going to be? What's the first kinematic equation going to be? First angular kinematic equation going to be the analog of number 1?
Would that be omega is equal to omega naught plus alpha t?
Exactly. That makes sense. Can somebody else tell me what the second kinematic equation is going to be? Just by analogy.
S equals S naught plus omega t plus
Right,
1.
it has to be, you're almost right, it has to be angular variables. So what is the analog of position from our table over here?
Oh, my bad, I missed the track. Theta.
Yeah. So yeah, very good. So go ahead. Theta final is equal to?
Theta final equals theta initial plus alpha t, or not alpha t, omega t plus 1.
Omega naught t, initial omega t plus, go ahead.
Omega naught t plus 1/2 alpha t squared.
Very good. That's exactly right. And I need one more volunteer to give me the third kinematic equation.
Omega final squared is equal to omega initial squared plus 2 times alpha times change in theta.
Yes, very good. Theta initial, theta final minus theta initial. That's exactly right. So you get these exact same kinematic equations, and I'm skipping the proof of this, though the proof of this is really, really simple. You get exactly the same kinematic equations that you do that we did for one-dimensional linear motion, right? So you can have kinematics problems which are very, very analogous to the kinematics problems that you did for one-dimensional motion back in chapter 2. So I'll give you, I'll show you one example of that. Oh, and another thing is, usually you can choose theta naught, the initial theta, to be 0. So if an object is starting from this particular position where its angular position is theta naught, you can just orient your reference direction to be this direction. And so you can always make the initial theta to be, you can choose the initial theta to be 0 usually. So that sometimes makes things a little bit easier. Okay, so unless the initial theta is specified, you can always choose theta naught to be 0. So that makes these equations a little simpler. All right, so let's look at an example of a problem. And remember that there is really nothing special about this. It's just very, very analogous to one-dimensional kinematics that you did in chapter 2. So I'll let you read this problem for a second. Okay, my first question is, what is this quantity that they've given us, this 0.187 radians per second square? Which quantity is that?
Is that our alpha?
Yes, it's the angular acceleration. Is it constant?
Yes.
Yes, they've given us that it's accelerating at a uniform rate. That means alpha is constant. Alpha is 0.87 radians per second square. All right. So that means since the alpha is constant, that means we are good to use angular kinematics, right? So the same considerations apply. So linear kinematics was only relevant when the linear acceleration was constant. Same thing with angular kinematics. It's only valid when the angular acceleration is constant. All right. So let's see. So we know the time interval. So our delta t or t, if you just take initial time to be 0, the time interval is just t. So that's 0.5 seconds. And it reaches its constant operational speed. So what is the initial omega angular velocity?
0.
Yes, because it's starting from rest. And it reaches a certain final omega, which we don't know. I think we have to find that. Yeah, so second part, we have to find that. We can always assume that it's starting from an initial angular position of 0. So we can take theta naught to be 0. And which quantity are we looking for over here? How many revolutions does the plate make before reaching its operational speed? So what quantity are we looking for over there?
Are we looking for a final theta?
Yes, we are looking for a final theta, but they don't want the theta in radians. They want us to convert it into the number of full revolutions, right? But that conversion is not a problem at all because how many radians is one full revolution?
2 pi.
Exactly, 2 pi. So theta, the final theta is what we are looking for in the first part of the problem, right? All right, so just the way you would do a kinematics problem, which equation can I use to solve for the final theta?
Can we use the second one?
Yes, so final theta is equal to initial theta plus omega 0 t plus half alpha t square. So all you have to do is just plug in everything. So theta initial is 0, omega initial is 0. So we just need to do half times 0.87 times 0.5 square. And that will give us our final theta in radians. We just need to convert it into revolutions. So you divide that by 2 pi and make it into revolutions. That makes sense? And to do the second part of the problem, what is the operational angular and the operational tangential speed? So let's do the operational angular speed, which is the final omega. So how can I find the final omega? Which equation will help me find that?
The first one?
Yes, I know the time. So omega final is equal to omega initial plus alpha times t. So you can easily find the final omega from there, right? And what is this? How do I find this thing? Operational tangential speed.
Could you do V equals R
V equals R omega, exactly. So they're asking for the tangential velocity over there. And we know that it's V equals R omega. That makes sense? All right, so that's all there is to one-dimensional kinematics. Oops. I mean, all there is to angular kinematics, and it's the same as one-dimensional kinematics. All right, so I have a couple of other examples over here. I marked this problem as optional, but there is absolutely nothing difficult about this problem, so you can do it easily. It's based on this funny video clip, but yeah, there's really nothing difficult about this problem at all. All right, the last topic in this chapter is this very important topic of rotational inertia. Okay, so what is rotational inertia? Now, we talked about the concept of inertia back in chapter 4, I think. And we said that inertia is the tendency of an object to either stay at rest or remain moving in with uniform velocity, uniform motion in a straight line, right? So that's basically Newton's first law. So inertia is the property of matter which makes it obey Newton's first law. So as a result of inertia, a moving object just wants to keep on moving forever, and an object at rest wants to stay at rest unless you apply some force and make it move, right? Now, there is also a different type of inertia which applies to rotation. So when an object is at rest, you will have to it will not just start rotating. If it's at rest, it will just want to stay at rest. And if it's already rotating, then it will always just want to keep on rotating, right? You would have to do something to it to change its rotational state. You would have to do something to it to make it rotate faster or make it rotate slower. But if it can just rotate, if you just set it rotating and there is no other influence on it, it will just keep on rotating forever, right? So this tendency of an object to resist any change in its rotational state is called rotational inertia. That makes sense? So now let's look at an example of this. So suppose you have, let's take an object that can, a system that can be rotated. So suppose our system just consists of a very light rod and a point mass, but the point mass is heavy, but it doesn't take any spatial extent. It's just a heavy mass which takes up very little space. So this is, and it's pivoted around the point O. Now this thing can be rotated. So you can rotate the point mass in a circle like this. Now you know that depending on how much mass you've got over here and what the length of this rod is, it could be easy or difficult to rotate it, right? So for example, if you increase the length of the rod but keep the mass the same, do you think it'll be easier to rotate this or harder to rotate this? Which would take more work to rotate? If the radius is large, if the radius is large, or if the radius is small? In which case will it be easier to rotate?
When it's small.
Smaller.
Yes, if the radius is smaller, it will be a lot easier to just give it a spin. If the radius is large, it will take more work to rotate it. That makes sense? So you can see that the rotational inertia in this case does depend on how far away the mass is. And also, if you, for the same radius, if I tremendously increase the mass, if I put a huge mass over here, I mean much more massive mass over here, it's a point mass, so it doesn't take up, it takes up the same space. That would be much harder to rotate as well. That makes sense? So for a very simple system like this, we can see that the rotational inertia depends on, or which is a measure of how hard it would be to rotate it or how hard it would be to stop it from rotating. That depends on the mass, and it also depends on the radius of the circle that it's describing, right? So for a point mass, the rotational inertia, the symbol for rotational inertia is I. And by the way, rotational inertia is also called rotational inertia is also inertia is also called moment of inertia. And I use both of these terms synonymously. You can call it whatever you like, moment of inertia. So the rotational inertia of a point mass, the symbol is I, is defined as m times r square. It's the product of its mass and its times the square of its distance from the axis of rotation. So it's very important to understand what this r is. It's the distance from the axis of rotation. That is the moment of inertia or the rotational inertia of a point mass. That makes sense? And you can see that this formula kind of makes sense because we saw that if you increase the mass, the moment of inertia increases. And if you also increase the radius, the moment of inertia increases as well. It's harder to get it to rotate. Or if it's already spinning, it's harder to make it stop if the radius is very large. Whereas if the radius is small, it's much easier to get it to stop. That makes sense? So the definition of the moment of inertia of a single point mass, which is at a distance r from the axis of rotation, is m times r square. Is everybody clear about conceptually what moment of inertia means? All right. Okay. Now, how do I find the moment of inertia of an extended object? So we know how to find the moment of inertia of a single point mass that's going around in a circle about an axis which comes out of the page. But suppose you have, instead of a point mass, suppose you have this irregular shaped object, which is rotating about an axis which passes through this point O, and the axis comes out of the page. So this irregular shaped object is rotating in the plane of the page. So how would you find the moment of inertia of this? Conceptually, the way you do it is as follows. You break up this object into tiny little segments. Call each segment as, okay, let's say that this first segment, I'm just calling it delta M1. Delta just means it's a very tiny little segment, and it's at a distance r1 from the axis of rotation. So the moment of inertia of this first segment would be delta m1 r1 square, using our formula for the point mass, right? And so how would I find the moment of inertia of the whole thing? I would just do the same thing for every segment that's there. So I would basically do summation over all such segments, delta mi ri square. That would give me the moment of inertia of the whole thing. So I've just broken it up into these small segments. I'm treating each small segment as a point mass and just applying the formula for the moment of inertia of a point mass to calculate the moment of inertia of every little segment like that, and then just adding them up. All right, now to make this exact, I have to make sure that these delta m's are as small as I possibly can make them, right? So because if I have large segments, I can't call them point masses. So I want to make these delta m's as small as possible. So if you do that, you'll get the moment of inertia of the whole thing. So you just have to make sure to take the limit delta m tends to 0, so that you get, so that the segments that you're breaking it up in are as tiny as possible. Now
Professor,
this
this is
sum,
something that's not moving in a circular option.
yeah, go ahead.
This rotational inertia is for something that's not moving in a circle.
No, this is moving in a circular. So this disk is spinning about an axis through the point O. I mean, this shape is spinning about an axis through the point O. That makes sense?
Yes, I'm just wondering what's the difference in this case between the extended object and the point mass.
Okay, so let me just redraw that over here. So here's my extended object, and it's rotating about an axis through the point O. So the whole thing is spinning around this axis. That makes sense? So it's kind of like this. So if my notebook is the extended object and the pen is the axis, then it's rotating like this. Does that make sense? Yeah. And so what I did was I broke this into little segments. So I can think of each little segment as an individual point mass that's rotating around that axis. Do you agree with that?
Yes.
Yeah, and so I know how to find the moment of inertia of a single point mass. So if I know the mass of this little segment, delta m1, let's say, and if I know its distance, r1, then I know how to find its moment of inertia. It's just going to be delta m1 times r1 square. That's the moment of inertia of just that one little square that I've made, right? And so to find the moment of inertia of the whole thing, I just need to sum over all segments like this. So it would be delta mi ri square. That would be the moment of inertia of the whole shape. Is that clear? Any questions about that? And I just made one little qualification that if to get an exact answer, I really want to make these as small as possible, because the formula that I'm using, mr squared, strictly applies to a point mass. So I'm doing limit delta m tends to 0, delta mi tends to 0, summation of this delta mi ri square. That is the moment of inertia of the whole thing. Now, this particular summation, you know that when you take a limit of a sum in math, it becomes an integral. So this just becomes integral r square dm. So that means where dm stands for these delta m's, which you've made so small that they are infinitesimal. So this is the actual formula for the moment of inertia of an extended object. That makes sense? So what I'm doing, just to reiterate that, so I have this extended object which is rotating about an axis through the point O, and I'm considering these infinitesimally tiny little segments, which I'm calling dm, out at a radius r. And so the moment of inertia of one of these would be dm times r squared. That's the moment of inertia of a point mass. And if I sum them all up, which means if I take an integral, then I get the moment of inertia of the whole thing. So that this integral is the definition of the moment of inertia of an extended object. Okay, let me know what questions you have. So to summarize what we just discussed here, moment of inertia measures the tendency of an object to resist changes in its rotational state. And to give you an example, suppose you have this heavy disk which is spinning, that will have a lot of moment of inertia, right? A high amount of moment of inertia. And it would be difficult to, if it's spinning really fast, it'll be difficult to get it to stop. Whereas if you have a little CD which is spinning really rapidly, you can easily make it stop, right? So moment of inertia is a quantity which measures the tendency of an object to resist changes in its rotational state. And the moment of inertia of a point mass is given by this little formula, where R, what is R here in this formula?
The distance from the axis of rotation.
From the axis of rotation. And if you have an extended object, you can use the same formula, but you have to sum over, you have to basically break up the object into point masses, calculate the moment of inertia of each individual point mass and sum over all of them. And that will give you the moment of inertia of the extended object. Okay, so that's what we discussed so far. Everybody clear? All right. I have an example problem here where you just plug and chug into the moment of inertia of a point mass. So I'll let you do that on your own. Now, rotational inertia is analogous to mass. Actually, I should say is analogous to inertia, the inertia that we studied in chapter 4. Both inertia and rotational inertia depend. Okay, yeah. So rotational inertia is analogous to the old inertia that we studied in chapter 4. But there is one difference between rotational inertia and inertia. So inertia that we studied in chapter 4 depended only on the mass. So more mass means more inertia. Rotational inertia depends not just on the mass, but also on how that mass is distributed relative to the axis of rotation. Remember that the formula for rotational inertia is summation delta mi ri square, right? So in other words, you're breaking up the mass into tiny point masses and then evaluating the moment of inertia of each point mass and then adding them all up. So it does depend on how that mass is distributed. That makes sense? Let's look at an example of that. Suppose you have two objects. One of them is a disk, like one of them is a square, solid square like this, and the other one is a square, but it's more a frame. So this inside part is hollow. So you have a solid square over here, and you have a square frame over here. Let's say they both have the same mass. Which of these would have more moment of inertia about an axis which passes through the center of these?
The one on the right.
So please answer in the chat. So this is the solid square, and this is the frame. So just put in either solid or frame in the chat. Which one has more moment of inertia? And they have the same mass and same dimensions. The correct answer, very good. The correct answer is the frame. Why is that? Because just imagine, just think about the formula for moment of inertia. It's the sum. You can either think in terms of the sum or the integral, it doesn't matter. Delta mi ri square, where and sum over all I. So which means that you're breaking this up into these little tiny pieces, calculating the moment of inertia of each of these little segments, and then adding them all up to get the moment of inertia of the whole thing. Now, for the solid, you'll have many pieces which have small r's, right? Many pieces which have very small r's because they're pretty close to the axis of rotation. So when you evaluate the sum, many of these pieces will not contribute much to the sum because their r is very small, right? So you will not get a larger number overall. Whereas if you imagine doing the same sum for the frame, all of your little pieces that you're considering will be quite far away from the axis of rotation because the inside part is completely hollow. And so all of these will have large r's, right? And so when you evaluate the sum, you will get a larger number as the answer. That makes sense? Because all of these r's will be large. Whereas for the solid square, many of these r's will be small. And so they'll not contribute a lot to the sum. So the point is that in general, when you have more mass which is away from the axis of rotation, you have a larger rotational inertia. That's an important thing to remember. So if the mass is distributed further away from the axis of rotation, that increases the rotational inertia simply because of the way the rotational inertia is defined. Everybody clear about that? Final point is something we've already discussed. A higher rotational inertia means a greater resistance to having its rotational state changed. And that could either mean that if it's at rest, getting it to rotate, or if it's already rotating, changing the state of rotation by speeding it up or slowing it down. It's more difficult to do it if the rotational inertia is greater. That clear to all of you? All right. Now, we talked about this integral over here, which you can use to calculate moment of inertia. The good news for you, or maybe bad news for you, I don't know, is that you don't have to do this integral for this course. You can use this integral to calculate moments of inertia of all of these shapes, but you don't need to, because you can just use this table to look up moments of inertias of various shapes. In this table, you're given the moment of inertia of a given shape about a particular axis. Notice that the moment of inertia totally depends on what axis you're calculating it about, right? Do all of you agree with that? The moment of inertia depends on the axis, because it's a sum again. It's this sum, and all these r's are relative to whatever axis you're using to calculate. So if you use a different axis, then that changes all the r's and you'll get a different moment of inertia. So in this table, the moments of inertia are specified, and also the axis about which it's being calculated is specified. So as an example, the moment of inertia of this hoop about an axis which passes through its center and is perpendicular to the hoop like this is mr squared. But if you choose a different axis, you will get a different value for the moment of inertia. So unless the axis is specified, moment of inertia is meaningless. Here is the moment of inertia of a cylinder about its central axis, and that is half mr squared if the mass of the cylinder is m and the radius is r. So this table gives you moments of inertia of different shapes. So you'll be using cylinders a lot, discs, cylinders. We'll be using this one a lot as well, sphere. So the moment of inertia of a solid, actually, this is the solid sphere. So the moment of inertia of a solid sphere is 2/5 mr squared. That makes sense? There's a much nicer table in your textbook. This is from a different textbook. I keep thinking of switching it to the one in your textbook, but I keep forgetting. So your textbook has a much nicer table, which has these same figures. So you don't have to use calculus to calculate these. So you can always use this table to look up whatever moment of inertia you need for whatever shape you're working with. That clear to all of you? But conceptually, these all come from this integral, r squared dm, which is basically the moment of inertia, basically integrating over the whole shape, starting with the fact that the moment of inertia of a single point mass is mr squared. So that's where all those formulas come from. All right. Let's look at some examples. So remember that something that has higher moment of inertia is harder to rotate, right? It's harder to change the state of rotation of an object that has more moment of inertia. There are many practical applications of this. So a tightrope walker carries a long pole to keep themselves balanced. One of the reasons why a pole helps is the following, that so this is the tightrope walker, and let's say that they're walking out of the page and they're standing on this rope. This is the rope that they're somehow standing on. And so they could either rotate this way or that way if they're falling, right? Imagine that the rope comes out of the page and they're walking out of the page towards us. So in order to prevent themselves from falling, what they can do is they can increase their moment of inertia by holding on to this long pole. So this pole increases their moment of inertia because now they have more mass distributed away from the axis of rotation. And so that increases their moment of inertia, and it makes it harder for gravity to rotate them either one way or the other. That makes sense? So that is one application. Another thing is that another similar application, practical application, is that if you're about to lose balance and you're falling, you will notice that you have a tendency to spread out your arms like this if you're falling and if you're about to lose balance. So why do you do that? The reason that you do that is because when you spread your arms out, what are you doing to your moment of inertia about an axis which passes through your feet? Are you increasing it, decreasing it?
Are you increasing it?
You're increasing it, exactly. So if you're again like the tightrope walker, suppose you're about to lose balance, you're standing on one foot or something like that, and you're about to lose balance. If you spread out your arms, you are increasing your moment of inertia about an axis which passes through your foot and comes out of the page. You're increasing your moment of inertia, and as a result of that, it makes it harder for gravity to rotate you about that axis. And there's a demonstration that I'll put up a video for. I'll put up some demonstration videos for 6 and 7 and also this chapter today. I mean, yeah, 8 and 9 as well today. So suppose you have a top heavy object. So I usually make a top heavy object in class by just attaching a heavy mass over here on this rod, and then ask students whether it's easier to balance this rod on my finger like this, I mean at point A or point B. So so which one would be easier to balance on my finger? So suppose my finger is over here. So should I keep would this be easier to balance on my finger, or would this be easier to balance on my finger? Which do you think would be easier? So this is where my finger is.
Would it be the one on the left?
Yes, that's exactly right. And why is that?
Because there's more mass distributed farther away from your axis.
Exactly. So this has a greater I, and this arrangement has a lower I about an axis which passes through the point at the bottom, which is where my finger is. So I want a greater I because I want the object to have more rotational inertia. So when it starts falling, I will have more of a chance to right it, right? Whereas if it has a lower rotational inertia because most of its mass is at the bottom, then it can very easily topple and I won't have enough time to right it. So this the one on the left turns out to be very easy to balance on my finger, but the one on the right turns out to be very difficult to balance on my finger. And I'll show you a video of that. I'll upload a video later today. That clear to all of you? There's another interesting example of this, application of this. Why do we bend our legs when we are running? So you will notice this. Suppose you're late for class or something and you're trying to walk as fast as you can. You will notice after walking for a little bit, power walking for a little bit at the fastest speed that you can, you will notice that it's much more comfortable to jog at the same pace than it is to walk at that high speed, right? So you will find that after a while, it's easier to just jog at that same pace than it is to walk at that very high speed. So why is it easier to jog than it is to walk? Now, when you are walking, your leg is straight, right? So this is your leg. This is the axis of rotation, which passes through your hip, and your leg is basically swinging about that axis, right? When you're walking. Now, when you're jogging, what is the difference? When you're jogging, your leg is bent like this. You keep your legs bent while you're jogging, and now you're swinging this bent leg about that axis, which passes through your hips. Which of these has greater moment of inertia, straight or bent?
Would it be bent?
Greater moment of inertia? Think about more mass away from the axis of rotation means more rotational inertia, right? So which has more mass distributed further away from the axis of rotation?
Your straight leg.
The straight leg, exactly. So the straight leg has greater moment of inertia than your bent leg. And that's why it's easier to swing your bent leg, and that's what you do when you're running, versus swinging your straight leg. That makes sense? So that is why it's at the same speed, it's easier, it's much more comfortable to jog than it is to walk. You can try this out. Just try to walk as fast as you can and then jog at that same speed, and you'll see it's so much easier to just jog than it is to walk, right? Okay. All right. So these are some practical applications. Okay, let's try this clicker, this top hat question. All right, please put in your answers. Okay, so I'm closing the poll now. So the correct answer is the disk. And actually, let me just demonstrate this first. So let's see if this video still works. All right, so
one of them is going to rotate more quickly. Let's see which one that is.
so as you can see, the disk clearly wins the race. And why is that? Because the disk will have a lower moment of inertia than the ring. And it's exactly the same reason that we discussed when we were talking about the solid square versus the frame. So for the disk, the moment of inertia is, if you imagine calculating this moment of inertia, is summation delta mi ri square. So, and the delta m's are these little pieces. So for the disk, many of these delta m's will have fairly low r's because they're the ones that are close by. So they're not going to contribute a lot to the sum. Whereas for the ring, what happens is that all the delta m's will be far away, will be at least some minimum distance away from the axis of rotation. And so the same sum for the ring will give you a much larger answer because the radiuses of all of these pieces are going to be large. Whereas for the disk, since it's solid all the way, radiuses of some of the pieces will be quite small. That makes sense to all of you? So in a shorter way of seeing that is that the ring has more mass distributed away from the axis of rotation. So it has a larger rotational inertia, and this has a smaller rotational inertia. And so it's easy for gravity to spin up the disk than it is to spin up the ring. That clear to all of you? All right. So I have some example problems over here. The last important concept in this chapter is how do you calculate the moment of inertia? How do you calculate the moment of inertia? So I told you that the moment of inertia can be found by looking up the table, right? But sometimes you might have a situation like this. Suppose you want to find the moment of inertia of this disk, but about an axis that is perpendicular to the disk, but passes through the point A. So you want to find the moment of inertia of the disk about an axis through the point A, and it's perpendicular to the disk. All right. Now, so you go to the table. So let's go to the table and see what we can find out. So we go to the table, which is right here. And so solid cylinder or disk. So this is the one that we want to look at over here. And we find that the moment of inertia is half mr square, but the axis happens to be the one that passes through the center of the disk or the cylinder, right? So that is not what our problem is asking us to find. So if I had to find the moment of inertia about an axis that passes through O, and we're given the mass and the radius of this disk, so it's r and the mass of the disk is m. So if I had to find the moment of inertia about an axis through O, then I could just report what's in the table, which is half mr square. But I have to find the moment of inertia about an axis through A. That makes sense? So the question is, how do I do that? For that, there's a very useful theorem called the parallel axis theorem, which I'll again state without proving it, though the proof would really be a bit beyond the scope of this course. Parallel axis theorem, which says the following: the moment of inertia about an axis. So you have the moment of inertia about an axis which passes through the center of mass. So let's call that ICM. So that's the moment of inertia about an axis through the center of mass. Suppose you want to find the moment of inertia about some other axis, any random axis, which happens to be parallel to the center of mass axis, right? Then these two moments of inertia are connected by this simple equation. I is equal to ICM plus a little correction, and that correction is the mass of the object multiplied by the distance between the two axes squared. So in this case, this would be the distance between the two axes, and the two axes have to be parallel. So the center of mass axis is perpendicular to the disk, and so is the axis that we are interested in. So the parallel axis theorem only applies to axes which are parallel to the center of mass axis. And so the answer would be ICM plus MD squared. So let's go ahead and calculate this. So in terms of M and R, what is the ICM according to our table? Does anybody remember?
1/2 mr squared.
1/2 mr squared would be the I center of mass, plus md squared. So m is the mass of the disk, and what should I use for d? What distance is that?
The radius of the circle.
Yes, exactly. And so the answer would be 3/2 mr squared. So to find the moment of inertia about an axis parallel to an axis that passes through the center of mass of the object, you can use the parallel axis theorem. That makes sense to all of you? All right, so that's really all that we need to know in this chapter by way of theory. I'll just do this one example, which all students, it's in your mastering physics, but all students seem to struggle with this particular example. And that's all that we need to do. I think it's probably a good idea to just do the exam on chapters 6, 7, and 8 and not to chapter 9. Do you think that's a good idea? Okay. So yeah, let's just do that. So let's put chapter 9 in the next exam. And so the exam will be chapters
That would
6,
be a
7,
good
and 8.
idea. Sorry.
Sorry, what's that?
I think that would be a good idea, personally.
Oh, okay. All right, good. Okay. So the homework for chapter 9 will be due next week, not next Friday, not this Friday. Yeah, because I think it's probably too much. We covered a lot of information today, and just for you to digest all that and take an exam on it tomorrow is a lot. But that's how these summer courses are. So there's really, you don't have a choice here. I don't either. Okay, so but I think we'll just do that. We'll take it easy on this exam and just make it 6, 7, and 8. And then 9 will be the next exam will be whatever we finish by next Thursday. All right, okay. So let's do, and another thing is, since we didn't have too many questions last Friday, I think what we'll do is we'll have a lecture for the first half of tomorrow's class, and then the second half we'll use for review. That makes sense? So the lecture will be, we'll just continue. We'll finish up whatever we have left chapter, the next chapter for the first hour, and then we'll do a review for the second half tomorrow. Okay, so let's just do this problem. So we have an equilateral triangle which is constructed using 3 vertical rods, and each rod has a length L and a mass M. And you have to calculate the rotational inertia of this structure about an axis which, so this should be inertia of this triangle. So you have to find the rotational inertia of this triangle about an axis which passes through one vertex and is perpendicular to the plane of the triangle. So you have to find let's say that this is the vertex, O, let's call this O. So you have to find the rotational inertia of this triangular structure about an axis which passes through O and is perpendicular to the plane of the triangle. So any thoughts on how we can do this?
Use parallel axis theorem.
Yes. So the first thing that would be useful to know is to find the moment of inertia. Let's do this. Let's do a smaller sub problem first. And I think that's all we'll have time for today. Suppose I have this rod of length L and mass M, and I want to find out its moment of inertia about an axis perpendicular to the rod and passing through one end, right? So suppose I want to find that. Now I can go to the table and I can find the moment of inertia of a rod which is about an axis passing through its center and perpendicular to the rod. So that is something that's in the table, and I'll just tell you what the answer is. But you can look it up in the table and verify too. So the moment of inertia of the rod about an axis which passes through its center of mass and is perpendicular to the rod is 1/12 ml square. That makes sense? Now, can somebody help me find out the moment of inertia? So that's the ICM. Can somebody help me find the moment of inertia of this rod about an axis that passes through A? Then how would I do that?
You could use the moment of inertia of the center of mass and then add the mass times the distance from.
Yeah, the distance between the two axes. Very good. So I can use the parallel axis theorem. So the moment of inertia about an axis which passes through A is going to be ICM plus a correction, which is the mass of the rod, times what should I put in for the distance between the two axes? In terms of the length of the rod is L.
Is it just L?
So what do you think is the distance between the two axes?
Would it be L cosine
No,
30?
okay. So your brains are officially fried, it seems. I'm asking for this distance, and the total distance is L. That's L.
Oh, so it's just L minus AO.
The point O is at the midpoint of the rod. Yeah, it's L divided by 2. That makes sense? That clear? So this is just going to be L divided by 2. Is that clear to all of you? Alyssa, is that clear?
Yes.
Okay. So yeah, so now we can finish this. So it's going to be 1/12 ml square plus ml square divided by 4, right? And you can simplify that. 1/12 ml square plus 3 ml square divided by 12. If you multiply both sides by, multiply top and bottom by 3, and then that becomes 4 divided by 12, so 1/3 ml square. And this is a very important result. It's not in the table, but this is a very important result which you'll use a lot in doing problems. The moment of inertia of a rod, thin rod, about an axis which passes through one end of the rod and is perpendicular to the rod is given by 1/3 ml square. And the moment of inertia of a rod about an axis which passes through the center of the rod and perpendicular to the rod is given by 1/12 ml square. That makes sense? So the 1/3 ml square just comes from applying the parallel axis theorem. Is that clear to all of you? One very last thing before I end the session. So yesterday we talked about center of mass, and we found the formula for calculating the center of mass. It was MI/XI divided by M. That was XCM, and you have similar formulas for YCM and ZCM. I forgot to mention that this will allow you to find the moment of the center of mass location of a set of points, or point masses. But how do you find the center of mass of an extended object? So if you have a rigid object like this, how do you find the center of mass of that? So that is a process of integration, which we didn't discuss in class. But you should know that conceptually, as a result of these formulas, the center of mass will be at a location where you have more mass, because these are kind of like weighted average formulas, which is weighted by mass, right? So as an example, suppose you have this uniform rod, which is the mass is uniformly distributed. Where is the center of mass of this going to be?
The center of the rod.
At the center, exactly, if the mass is uniformly distributed. If you have two uniform rods, one of them is made of metal and you stick it to another rod over here, which is made of wood or plastic. It's light. So where do you think the center of mass of this composite rod is going to be?
Somewhere within the metal part.
Exactly. Because so wherever you have more mass, you have the center of mass will be closer to that region, right? And finally, if you have a donut where this mass distribution is uniform, is the center of mass of this donut going to be?
In the center.
In the center, exactly. So if a shape happens to have a nice geometrical center and the mass is distributed uniformly, then the center of mass will be at that center. Right? All right, so that's it for today. If anybody has any questions, I can answer them. This is a very important chapter, and these topics are all very important. So yeah, so we will have a lecture for 1 hour tomorrow, and then we'll have the review session after that. And the exam will be up till chapter 8, and I'll reset the deadlines for mastering physics, so it's not due this Friday. It's going to be due next Friday, right? So if anybody have any questions?
Could you scroll? Oh, sorry. Could you scroll back to where we solved the moment of inertia for the axis on the end of the rod?
Yeah, this one.
Thank you.
Everything clear about this?
Yes, I think my algebra was wrong in combining the fractions. I was just
okay. Yeah. So this 1/4 you make into 3/12. That's correct, right? 3/12 is 1/4. Yeah, and then you do 3 plus 1 in the numerator.
Yeah.
So you have 4 divided by 12, which gives you 1/3.
Thank you.
Any more questions?
I just had a question. Will the exam window be the same as last time?
Yeah. Okay. Any more questions? All right. So if there's no more questions, I'll see you tomorrow. And I will do an office hour tomorrow as well. So 12, usual time, 12:15 to 12:45, if anybody has any questions. Okay. All right.
Thank you.
Thank you.
All right. Bye.
Thank you.